This is the first of 3 lectures on Chapter 9, Analysis of Variance, also called ANOVA, and specifically this is the one-way analysis of variance, which is distinct from what we'll be doing in Chapter 10. So consider an experiment. The research question is this: are people more likely to assume that an accused criminal is guilty when they know the person has a criminal background? So the experiment was set up like this. 15 individuals were given background information about a woman accused of passing bad checks. Then they were shown a DVD of her trial. The background information was identical for everyone except for one piece of information, which was randomly varied. So Group 1, criminal record, got an info sheet stating that she had a record of check fraud. Group 2, no criminal record, their info sheet stated that she did not have a criminal record. And Group 3 was the control condition, and the info sheet didn't say anything at all about her record. How could we test these 3 conditions? We know we can't use an independent t-test because it only allows us to compare a dependent variable guilt between 2 groups. But we have more than 2 groups, we have 3. ANOVA allows us to compare a DV like guilt across multiple groups. That's what this content is about. So what is ANOVA? It's called Analysis of Variance, and we'll talk about that more in a minute, but for now let's think about what the hypotheses are in an ANOVA. And the null hypothesis is always this: several populations all have the same mean. So we might state it like this. We might state the null hypothesis like mu1 is equal to the mean of our dependent variable. The mean for group 1 is equal to the mean for group 2, is equal to the mean for group 3, all the way to however many groups we have. That's the assumption. We're always starting there. None of these groups are different. And we might say it in words like this: the mean guilt rating by those in the criminal record condition is equal to the mean guilt rating by those in the no criminal record condition is equal to the mean guilt rating by those in the control condition. And so that's how the null is stated. The research hypothesis is a little bit different. We state it's just that at least one population mean is different. So we might say not all of the means for the groups are equal. We might state it that way. Or in words, we might say the mean guilt rating by those in at least one of the criminal record conditions is different. Why do we call it analysis of variance? It's because we're determining whether the variance between any of the groups is greater than the variance within the groups. So in this instance, you can see that the mean for group 1 doesn't overlap much with any of the other means. The means for group 2 and 3 do overlap quite a bit, and so we might be looking at, first off, what is the variance within the group, and that would be like the way you'd look at the normal distribution. I can't draw on this slide, but we'd be looking at the spread. And we'd be comparing, so we'd have a general idea of the spread, and we want to see if that spread within the group, so drawing a line along the bottom of one of these distributions, is different from the distance between these means. So let's look at the 2 types of variance more closely. Type 1 is within groups variance, variance within each population. And you can see the arrows drawn here showing the variability within groups. That's what we're looking at. And we're going to use formulas to find out what this variance would be. And these formulas will resemble things that we've used in the independent samples t-test. And so the test assumption is equality of variances, and once again, just like in the independent samples t-test, all we're doing is assuming that all of these samples, like the criminal record, the no criminal record, and the control group, that their variances aren't too different. If the variances are really different, then we have to take some different steps to do the test. So we do have that assumption here. In this particular within group variance is akin to the average of the variances within each condition. So that's what we're doing, figuring out the variance for each condition and kind of averaging them out. And whether we reject the HO or not, they're going to be that isn't going to be impacted. It just represents the normal differences in a population. We know that if we have a population and we draw different samples, even if it's one population, each sample, if we measure like their guilt rating, they're still going to vary in some way. And that's what this within groups variance is measuring. We also have between groups variance, which is variance between the populations. And so you can see here the within group variance that we talked about on the last slide is down below, and it's just like the variance in these spreads within each group. But the variance between groups is comparing these means, and so how far apart they are, and we're comparing all of the means with each other. And we could have, in the first example, we could see something where the null hypothesis is true. The variance between groups is equal to, or at least it's not greater than the variance within groups. And so that's what it looks like. We would consider these to be equal. They're not significantly, different. There's not much variance between groups. We can see there's a lot of overlap in these groups. This is probably a situation in A where we're rejecting the null hypothesis. The situation in B is one in which the null hypothesis is false. The variance between groups is greater than the variance within groups. And in this case, we can see that the variance within each group is really small, but the variance between groups, at least certainly between the blue and the green, is quite large. And that means that these differences in means represents both normal variation, the variation within group, and the impact of the treatment. We use a statistic called an F ratio. That's the statistic generated through an ANOVA test. And the formula is just, we're going to calculate between groups variance and divide it by within groups variance. You can see in the image that the distribution is skewed, and it's always going to be positive because we have a 0 right here at this end. The 0 means that there's no difference at all between the within groups variance and the between groups variance. So we're just calculating a ratio. And this is just a general image of what this distribution looks like. We have a cutoff point that we'll be looking up. We always are going to have a right-tailed test because we're testing the hypothesis that variance is different between the groups or it isn't. And so we're looking at a ratio, and it's always got to be greater than 1. So we'll get the cutoff point. And alpha 0.05 or 0.01, that will be the same, but it's always in the upper tail. The critical value, or what we have been calling the cutoff point, will be drawn in, and that'll be the F cutoff point, or we might call it F alpha, because that's what it's associated with, the F score linked to the alpha that we've decided. So if the ratio is 1 to 1, that means there's no difference in the means. If it's greater than 1, the means are different, but we ask the question, how much greater? And that's where this F point comes in. Statisticians have figured out exactly what the odds are given circumstances that we'll put in through our degrees of freedom. The F distribution, actually, just like our T distribution, changes shape as the degrees of freedom changes. We haven't talked about this yet, but we do have 2 degrees of freedom in the F test. We have 1 degree of freedom according to the number of groups, and the DF2, the other degree of freedom, according to the number of individuals minus the number of groups. And we do have more rigorous standards when the n is small. So we could see this very small n, we have really fat tails. In order to go where 5% of the scores are, we're going to have a pretty high cutoff point when we have a smaller n. And conversely, just like in the t-test, when we have more in our sample, the tails allow us to have 5% with a lower cutoff point. So it's going to be easier to get a significant F score when we have more in our sample. That's what the power determination is all about. There are some assumptions for the analysis of variance. First off, our DV has to be continuous. So it's best not to have like one item, Likert scaled item as your DV, like on a scale of 1 to 5, how much did you like this ice cream? It's best not to have that because we end up not being able to accommodate a normal distribution. We just don't have enough potential variability in our dependent variables. So it is best to use scales or inventories that have a little more than just 5 data points. No groups, this is a very important assumption, no group can be dependent on any other group. So what this means is if you think back to what we had for the paired samples t-test, we had, for example, one individual producing before and after scores. So we couldn't have that in ANOVA. We couldn't have someone producing a score in week 1 and a score in week 2 and a score in week 3 because each week's scores would be dependent on the other scores in a systematic way. Likewise, we couldn't have sets of siblings producing data, comparing data for sibling 1 and sibling 2 and sibling 3 because they would be related. So that's a really important assumption. We have to assume homogeneity of variances, and that just means that we don't want the variance in any one of those groups to be really a lot larger than the variance of the other groups. We can use that rule of thumb of 4, but we would still do that Levene's test of equality of variances to determine whether we meet this assumption. And finally, we assume a normal distribution for each group. And just as we did for the independent samples t-test, we would do similar calculations for the analysis of variance. So those are the assumptions that we have to meet. So practice 1 is going to be asking you to determine when an ANOVA is appropriate. And so here we have an example. People who are older than 40 will have poorer scores on a test of near vision than people in general. We can see that this is comparing these people who are older than 40 with people in general. We just have one sample, those older than 40, and that's a one sample t-test. People who walk every day at sunset will feel more relaxed in the evening than people who walk every day at sunrise. Someone hypothesized that. In this case, we have 2 different groups of people, those who walk at sunset and those who walk at sunrise. We only have 2 conditions. There's no other condition, and so this is an independent samples t-test. 2 conditions, we're going to stay with the t-test. Although I will note that if we did an f-test, we would get the very same score. People who read an article describing problematic female leaders will give poorer ratings to women in powerful positions than people who read an article about excellent female leaders or people who read a neutral article about a bridge. So in this case, we need an analysis of variance. That's because we're comparing 3 different conditions. First, those who read the article about problematic leaders. 2, those who read an article about excellent leaders. And 3, those who read no article. So with that said, you're ready to take your first practice quiz, and the next lecture will be how to conduct an ANOVA.